There we go. All right. Hi, everyone, and welcome to this RustLab webinar. We're really happy you could join us here virtually. And we have here Pietro Lorefice, our speaker for today. Hi, Pietro.
Hi, Latara. Hi, everyone.
Yeah, so let me tell you about RustLab this year. We're doing a series of events dedicated to Rust, the language promoted by Mozilla that has a lot of potential and allows everyone to create reliable and efficient software. And RustLab is organized by Develer. And Develer is the company that develops hardware and software in the industrial field with great focus on emerging and open source technologies. And they strongly believe in the role of training and collaboration. And because of this, it regularly organizes technology events such as conferences, workshops, and courses dedicated to technologies, such as our talk today, Rewriting a Small Component from C to Rust. So before we begin, I just have a few notes for you all with us being here. The first one is if you have any technical problems or if the connection is not good or if the streaming stops for any reason, please remember that you can join the webinar again using the email that you received. Just click on the join button in that confirmation email and you can re-enter this live room. Another quick reminder, stay tuned for the Q&A session at the end of the talk, and I would kindly ask that you all save your answers for the very end. We're going to have a dedicated chat room just for questions, so if you can save all those burning questions until the end, we would really appreciate it. And for networking, there is Discord, so you can join us there to also chat throughout the whole year, actually. We'll keep it going even after the events have finished. So enough from me. I'll leave you now in the hands of Pietro, who will talk about rewriting a small component from C to Rust. Have fun, and we'll see you for the Q&A. Thanks.
Thank you, Latara. Let me introduce myself. My name is Pietro. I work at Develer, the company that organizes this event. I'm a firmware developer, so I mostly deal with firmware development for microcontrollers, ranging up to writing board support packages and drivers for Linux-based boards, and basically everything in between. My daily programming language is mostly C, as you can probably expect from this talk. But I'm in the last 6 months or so, we started experimenting with Rust for some internal tooling and also for some production applications, as is the one that we will talk about today. So let's get started. Let me just share my presentation. Okay, just a second. Okay, there we go. Before we get started, let me just give you a brief introduction about the system that we're going to talk about. It's an ongoing project that we are developing for a customer. It's a project with more than 4 years of history, so it's actually quite mature right now. It's been used in production for a while now. But it has still features missing, so the development is still ongoing. It's basically your typical industrial system, so it's a distributed low latency real-time system. It runs on several pieces of hardware, at least a couple of custom boards running Linux, and one or more PCs. Each custom hardware runs from one to several processes, depending on its role inside the system, and everything is connected via Ethernet links, so there is a bit of socket programming involved. The project itself is comprised of many languages. I think that 90 to 95% of the code base is written in Go right now. The rest is basically an even split between C++ and C. So the component that we're going to focus on today, and that is the the subject of this talk. It's a very small component. It's written in C. It's about 1,000 lines of codes, more or less. Now it's up to 2,000 actually, after some recent features have been added. But it still accounts for less than 2% of the code base, and this is excluding unit and integration testing. So this is just the business logic. So as you can imagine, it's quite a large project. The component itself is a small system daemon, so it starts when the hardware boots, basically. It's single-threaded and sequential, as are most of these kind of low-level control software. An important point that we will stress later is that it's a low-latency system, meaning that it has strict deadlines that must be granted in order to have a working system, basically. The component was originally written in Go, and it has already been rewritten once in C, which is its current state, mostly due to latency spikes that were introduced by the garbage collector in Go, of the Go runtime. So it's already undergone a first rewrite. The application logic of this component is actually quite simple. It's basically a periodic execution loop. It's running at a fixed rate of 12 milliseconds, about 12 milliseconds. And in a single loop, it basically does a couple of things. It synchronizes with an external hardware event so that everything runs smoothly and on time. It updates the internal system based on some external state, which is basically data coming in from some device drivers and some network sockets. This happens until it's close to a deadline. So we are close to the 12.5 milliseconds deadline. At this point, the data received in the previous slot is processed according to the internal state, and then this data is written to a device file. So all in all, very simple. It's your classical control loop, basically. So there are a few requirements, obviously. It's a time-bound deterministic execution loop. One of the most important points is that the rate of deadline misses on this component must be extremely low. We are talking about a few parts per million at the most, because otherwise the system performance would degrade quite fast. So we need to basically always manage to respect our deadlines. For these reasons, and also for other, that I'm not going to go into too much detail about this, but one of the requirements is that the use of dynamic memory in this system must be quite limited. So when possible, static memory should be used, or at least automatic memory. We'll talk about this later. It needs to have minimal external dependencies. This is a choice that is it comes from two arguments, basically. The first is that being a custom designed operating system, adding and managing external dependencies is not that simple. And the fact that managing dependency in C is a pain, and we'll talk about this later. And it also needs to have extensive unit testing, simply because the component itself is very difficult to test outside of its working system. We have a simulator, but the scope of the simulator is limited compared to the whole system, so it needs to have an extensive unit testing performed on it. And to give you a rough number, basically, the amount of lines of code in the unit and integration tests is almost thrice the number of actual code written. So let's just jump into the main topic. Why was this component rewritten from C to Rust? There are several reasons, actually. The straw that broke the camel's back, as they say, is a couple of bugs that were extremely tough to manage to find and solve. But there are also several other arguments that we are going to go into detail about. So the first one, my first piece of beef that I have with the C programming language is that debugging using Printf, as probably most of you know, is the first frontier of code debugging. Before jumping into step-by-step debugger, most of us usually try to inspect the internal state by printing it out, basically. This is already difficult to do in this kind of systems because due to the latency requirements and the amount of data that must be processed, printing only a small amount of data is actually already quite hard. And C doesn't make it easier for us. If you have ever used the printf function in C, you may already know that it's actually quite hostile in terms of syntax. We have a whole bunch of conversion specifiers depending on the type of variable that we need to print. On top of that, we have several length modifiers according to the width of the parameter that we are going to print. And then there are also additional flag characters that basically completely modify the semantics of the conversion specifiers. And the most important limitation about printf in C, as you may know, is that it doesn't allow printing of compound types. So, for example, as you can see in the piece of code on the right, if you have a full structure, for example, containing 3 fields, 2 integers and a string, there is no built-in way to print the layout of foo in memory. We need to go ahead and print every single field one by one, or at least have some kind of helper function that prints the content of foo, which is unreasonable to expect from a large code base with probably hundreds of types. So we come to another pain point of the C programming language, which is the standard library, or rather the lack of standard library. Basically, the standard library in C is non-existent. It's extremely lacking in several areas, which are basically most of the areas that count when you need to work with an embedded system. So file system access, networking, threading, and concurrency. Basically, without all this stuff, you have a self-contained application that can do very little. There have been attempts in the years to address this problem. For example, the Posix library tries to fix most of these issues. The problem here is that the Posix library, for example, is not a portable library. It runs just fine on Posix compliant system, but for example, writing a portable C program that also runs on Windows is kind of a mess. Another problem with programs written in C is memory allocation. So before we go into detail about this point, let me just state something that probably most of you know. There are several allocation strategies in a program. This is independent of the language that we are talking about. There is static memory allocation, which is the allocation that happens at compile time, and it is used basically for static variables that last the entire lifetime of a process. There is automatic memory allocation that is basically stack allocation, which is used for local variables, and it happens automatically at runtime, and it is also managed completely by the compiler. And there is the most dreaded of them all, which is the dynamic memory allocation, which needs to happen explicitly at runtime, and it is used basically for allocating memory whose layout is not known a priori. So, for example, if we need to allocate space for a number of objects that needs to be determined based on some external condition, we need to use dynamic memory allocation. In garbage collected languages, dynamic memory is managed by the runtime, as most of you may know. In this case, the allocation happens implicitly. We're talking about languages like Python, JavaScript, and so on. In C, dynamic allocation is managed by the user explicitly using functions like malloc, free, and so on, and the malloc family of functions. And just to give you a sense of how hard it is to do dynamic memory management correctly in C, I will show you this example. This is actually a real example. Of course, it's a bit modified for the sake of the talk, but the content is basically one-to-one, of having a generic vector, which in C is already a fit in itself, writing something like this. which can be initialized for elements of a given size. It has a push function that allows to insert an element into the vector, and a destroy function that is basically a destructor for the vector, which deallocates the memory allocated dynamically at runtime. So let's assume that we need to use this vector in the code on the right. We have function foo that needs to fill up some vector and return it to the call. So the code is fairly straightforward. We initialize the vector. Let's assume, for example, that the vector will contain integer types, so int size types. We push 1 inside the vector and then return it. This is all good. The caller gets the vector, uses it in some way, and then forgets to call the destroy function. What happens here is that we do not have a reference anymore to the vector. The object is lost forever, but it still lives in memory because it was never deallocated. So we have what we call in the industry a memory leak, memory that has been lost forever that cannot be recovered anymore. So what can we take away from this example? Well, first of all, memory management is hard. It's probably one of the hardest things that we can do when programming, aside from concurrency. Mistakes in dynamic memory management are difficult to spot. For example, we will see later that this kind of bug took us almost a day to track down, and may go unnoticed for a long time, depending on the amount of memory that is allocated and lost and leaked to the bug. The software may go for days before it crashes or is killed by the operating system. And there are tools to inspect and solve these bugs. For example, valgrind is an example when using the C programming language. The problem is that these tools are difficult to use in unconventional environments. For example, if we have a minimalistic embedded system, building valgrind for a Linux-based OS, custom built, is actually almost as difficult as writing the code. So let's say that when it is possible, it's best to avoid it. And this is one of the reasons why the amount of use of dynamic memory in this project was as limited as possible. Dependency management. The tumbleweed is back. As you may know, there is no way in C, there is no built-in way in the C programming language to manage dependencies. There is no centralized package repository, so C libraries, when are available, are found on GitHub, on, I don't know, some FTP server somewhere. There is no standard tool for managing third-party libraries. There are workarounds depending on the environment. Some use, for example, Git some modules to track dependencies. Some just put together a build script that downloads them, extracts them, and builds them. And all of this gets even more complicated when doing embedded system programming, since we often need to build this dependency from scratch, from source, since we cannot use pre-built libraries, pre-compiled libraries. So dependency management is another pain point of the C programming language. Testing. Again, no testing facilities are built into the language. Usually, the common way is to just have a separate executable which runs a bunch of tests, and the exit code specifies whether the tests have passed or not. The problem here is that this allows to do some black box testing, but it's actually hard to do unit testing, for example, of private functions, which in some occasion we may want to do because, for example, in this particular scenario of this particular project, the public interface of the very few modules that are involved is actually very simple, and it is meant to be run as a black box. So unit testing in this case becomes quite complicated. There are frameworks, there are libraries, at least, so we have that. The problem is that a more integrated testing environment would be nice to have. A particular point in which I want to focus regarding testing is the is mocking. Mocking is a practice that is particularly important in embedded system development, and it basically involves the abstracting an interface, for example, something that communicates with low-level hardware that is not available in a testing environment, for example, in a CI. And so we just mock, hence the name, we mock the access to this hardware, we mock the hardware itself, and simulate its behavior. In C, mocking requires the API to be engineered in a specific way. For example, a standard way to do this is having structs of function pointers and private data fields inside the structure that we can replicate that we can replicate in a mocked structure. The problem here is that this makes the code much more complicated at the point where sometimes the mock interface is actually the abstraction over the actual hardware is actually more complicated than the hardware itself. So it would be nice to have something better than this. So these are all the problems that I have encountered while writing C programs. So at this point, one must wonder why Rust. Why we chose Rust as a replacement for this for C. Well, there are a couple of reasons, and I'm gonna list them basically in the same order that I list the problem of the C implementation. So first of all, Printf-driven debugging in Rust. It is actually very simple, very immediate. There is the same class of print function as are found in the C language. So the equivalent of printf in Rust would be the print macro. The difference here is that the format specifier uses a single formatter, which is the open and close curly braces, and a small number of modifiers for advanced formatting. And any type that implement the debug or display traits, and we'll talk about traits in a while if you don't know what they are, that can be automatically implemented for basically 99% of the types, allow to print a representation of a structure of a complex type, of a compound type, without having to write access functions and without having to go into details about the type. So for example, as you can see on the right, we have a similar structure to the full structure before. We have an unsigned integer, we have a string, we have a more complex type, in this case a range type, and printing foo basically prints what you see in the comment without any additional hoop jumping by us. I've talked briefly about traits. Traits basically, you can think about them as interfaces in object-oriented programming languages. They are not exactly the same thing. There are differences, but they are quite similar. Basically, a trait defines a shared behavior between otherwise different types. So it is basically a list of methods that, if a type implements a trait, are guaranteed to be present for that type. And Rust makes an extensive use of traits as a language feature since they are a very powerful mean of achieving something like object-oriented programming. So this is an example of a trait. We have a trait called animal, which has a single method. The method is canFly, which returns a Boolean value, which is true or false. So it's a trait with a single method. And then we implement the syntax here. The operation here is called implementation. We implement the traits for a type, in this case, the dodo type. And we implement basically the canFly method for the dodo type. And here we return the false value, since dodos can fly. So the constraint here is that a type that implements a trait needs to implement all of its methods, unless the trait already provides a default implementation for some methods. In this case, the trait implementation can choose to override it or leave it as its default implementation. So as you can see, it's very powerful because it can be used for achieving basically generic programming. Okay, You can think about this as similar to templates, for example, metaprogramming in C++. Next, let's talk about Rust Standard Library. Honestly, I think it's one of the best standard libraries I've come across in the various programming languages that I've used for some reasons. First of all, for being a systems programming language, the standard library is actually very, very extensive. We are talking about methods for accessing the file system, networking, so sockets and so on, concurrency, whatever. The best thing about this is that it is entirely portable to all platforms supported by the language, with very few exceptions for OS-specific functions that can also be gated behind conditional compilation. It's very well documented, and most of all, is consistent with itself, meaning that rarely you will encounter a function in the standard libraries which does something that you do not expect. Memory handling, and here we come to one of the main selling points of Rust, which is memory safety, basically at no performance cost. Why is this possible? Basically, the language has been engineered from the start to have compile time guarantees and a bunch of semantics that basically allow us to avoid most classes of memory bugs. If you think about the fact that in C programs, basically 75 to 80% of bugs are due to memory-related errors, you can get by yourself that this is actually a killer feature for the language. The nice thing here is that the user still has total control over what goes on the stack or the heap. So it is not a garbage collected language. There is no runtime that manages the memory for us. All this memory handling is basically done at compile time by the compiler. So the compiler knows when something goes out of scope and can free the memory for us, can insert the code required to free this memory for us. And this is an example, basically the equivalent example for the equivalent C example in Rust. We have the same foo function that in this case return a vec, which is the vector type in Rust. Another point that I did not make before, but it's actually quite important, the C standard library lacks basically any kind of collection types, which are instead present in Rust. And vector is one of them. So we create a single vector with a single element, 1, as before, and then we call the foo function in bar. In this case, we get back a v variable, an object that we bind to the variable v. We print the number of elements inside the vector, and then the vector goes out of scope. The point here is that the compiler that is able to detect that v goes out of scope and is able to destroy its content and does not leaks any memory. And this is actually what we want. We want automatic memory management without having to deal with low-level complexity. Notice that in this case, the vector is not stack allocated, so its content is actually allocated on the heap, but we do not need to do anything to manually deallocate this memory. The compiler does this for us. Dependency management. Dependency management in Rust is one of the most painless experiences that you will have, unless you do something complicated and weird. The website crates.io is basically Rust standard package registry. It is seamlessly integrated in Cargo, which is the build tool for the Rust programming language. And importing what in Rust is called crate, which is just a library, an external library, it's just a matter of writing a line in a manifest file. Okay, so you need to put a line, you need to know that a crate with that name exists, you specify the version, you can also omit the version if you want, you can specify the version, and the build tool will just download the crate for you, and you can start using it without any issue. Dependencies are versioned, which is important, especially when dealing with embedded systems. And this is a nice thing, can also be vendored. So Cargo is able to download the source code for all the dependency and their dependencies, so all the dependency tree, and put it in our repository where we can vendor it and use it 5 years from now if we want. Testing. Testing, unlike C, is a feature that is built into the language. So on the right, you can see an example of unit test, basically. We have a function. The function is called the answer. It returns an unsigned integer. The unsigned integer is 42. We want to write a test that asserts that the function returns the correct integer. We just write a simple function. We use the assert macro in it to basically equate two values. And then we just mark it as a test by putting that annotation on top, which basically instructs the compiler to build this function only when we are compiling tests. In any other case, the function is just silently ignored by the compiler. When running in test mode, the function is executed, and if the assertion fails, the executable exits with an error. This is an example of unit test. There is also support for integration tests. Basically, everything is supported out of the box. Mocking. We talked about mocking before for the C example. I think that this is an important point to make for Rust, because this is one of the most seamless ways of doing mocking that I've experienced. We basically define a trait. So, for example, here we want to mock access to a GPIO, for example, a general purpose IO pin, which has basically three functions. A direction function to specify whether the pin is an input or an output. We have a write function that basically sets a value on the digital pin, and we have a read function that allows us to read the value at the state of the pin. Simple as that. Three methods. Any type that implements a digital pin can implement this state, can implement this interface. So, for example, in our production code, we have a digital pin implementation, which we call hardware pin. Hardware pin will implement this function in a hardware-specific way. Then we have a function that we want to test that runs in production code that takes a pin. In this case, notice that pin is a generic type P, and with this syntax, P colon digital pin, we specify that P is any type that implements this interface. So we call toggle switch. The function will probably do something with the pin, more than likely sets its value via the write function. And then what we want to do is basically test this function, this toggle switch. So what can we do? In our test, on the right, we basically declare a structure, a new type. We call it mock pin. With just a Boolean value inside, we do not care about reading, setting direction, and so on. In this case, we just care about what gets written to the pin. We implement the digital pin interface for mock pin, and then after we run the test, we invoke the toggle switch function with our mock pin instance and simply check that the value written inside the pin matches basically our expectation with respect to the behavior of the toggle switch function. So as simple as that. There is no overhead because Rust is smart enough to avoid dynamic dispatching in this case. It uses static dispatching. So we have no overhead at runtime, and we have a simplicity of being able to test our hardware-dependent function in a CI environment, for example. So we are almost at the end. So this is the question that probably you are asking yourself right now. So should I use Rust, or more likely, when should I use Rust? And for this reason, I'm going to bring you some real-world example about this piece of software that I'm talking to you about. Examples of bugs where that could have been preempted completely if we had used Rust from the start. For example, bug number one, we had an initialized variable in an instance of the structure that was missed during a refactoring. So we added a new field and then forgot about initialization of this field when creating the struct instance. The problem here is that while tests were passing fine on the local development machine, they were failing in the CI pipeline. This is due to the fact that stack allocated objects in C are not initialized by default. So the value contained in the uninitialized field was basically random. And in my local machine, it was the expected value, which was 0, basically. But in the pipeline, in the CI server, basically, it had a completely random value. And it took a relatively small time, just an hour, to find the missing initialized variable. The problem here is that Rust would have prevented this bug completely, since in Rust, every field of a structure must be initialized at creation time. I cannot declare an instance of a full structure, for example, without filling all its fields. So this is one point for Rust. Bug number 2, this is the same bug that I've shown you before. So I'm missing 3 of a returned value, in this particular case, a vector. And the process was being killed by the kernel due to out of memory after several hours of running. So the problem here is not only that we had a bug, but it was also a bug that was difficult to reproduce because the amount of leaked memory in each cycle was a handful of bytes, basically. And it took us a long time to find this bug, almost a day of scouring for the bug, because it was so hard to reproduce. In Rust, this wouldn't have happened because, unlike in C, where dynamic memory management is hard, in Rust, memory leaks are hard. So it is very difficult to create a memory leak unless you are using unsafe code, of course. Bug number 3, and this was actually the reason why the software was rewritten in Rust. This took us 3 days to find, and we managed to find it only because we rewrote the software in Rust, and we saw that it was working, so we were able to narrow down the possible field of the possible scope of searching to just a few lines of code, basically. And this was due to the fact that we had an unhandled error return from a function which was deep into the execution loop. So basically an allocation was failing, and we didn't handle this allocation failure. And basically from there, the system made some assumption that caused a degraded performance over time, and also system stall under certain conditions. This also would have been prevented in Rust, since when using the default result type, the compiler will issue a warning when you do not check the value of the result. So you can either unwrap the result and trigger a panic in case the result was an error, or you need to explicitly check the result, and so you have to account for it, basically. Another class of bugs that would not happen in a Rust written software. There are also some nice-to-have features. These are not deal breakers when using another language, but they are nice to have. So, for example, Rust is a modern language, so it is being engineered with CI/CD integration in mind, mainly because we have a build system that is standard, so it allows us to leverage existing tools and existing environment. There is dependency management, so we do not have to manually handle our dependencies and so on. Also, and this second point is particularly important for embedded systems, switching target architecture is actually quite seamless. It's very easy to do. Rust supports cross-compilation out of the box, supports a very large amount of targets. Most of the time, you only need a linker for the target and you're good to go. So unless you are doing some complex, you have some complex build scripts and you need to set a sysroot for your build process, 95% of the time, it's actually quite seamless. What I learned from this experience? First of all, when doing systems programming, for me, Rust is basically a no-brainer. So it's almost best in class. So in a field where basically the strongest competitor right now is C or C++. In most other domains, it is still a very strong candidate. For example, computer graphics, for example, command line tools, and so on, because it's actually a very versatile language, in my opinion. Second point, my advice is to start small and expand from there, especially if you are new to Rust. Rust has a admittedly quite high barrier of entry, but despite this, Rust has great support for FFI and interoperability. It has many serialization crates. So basically what you may want to do is to identify a small component in your system, isolate it, and basically write only the small component in Rust. The interoperation with the rest of the system can be through foreign function interface, can be through serialization methods. So I don't know, JSON, any kind of data exchange type serialization method that you want to use, but it is doable. And finally, if possible, use Rust from the start. I say this because if you do a one-to-one porting of an existing piece of software, you may end up being swayed by the way in which you have already done your things. You have already implemented things. So it's usually best to start with a fresh mind and do things in a rustic way. Let's just say that. One thing that I missed and that I want to stress is the fact that this software, I was able to rewrite the whole software in just 3 hours, basically in an afternoon. And one of the most amazing things is that after I wrote the last line of code, I just built it. It built just fine. I just deployed it in our simulation environment, and it worked immediately. So without having to go back and fix stuff. So this, I think, is great. A great feature of Rust. Let's call it feature. The fact that most of the time, if you write something, that something will most likely work. So thank you very much. This was all, and if you have any question, I will be grateful to answer them.
Excellent. All right, everyone. So now we'll have the Q&A chat open so you can write all of your burning questions. We'll have a special Q&A chat just for that, and we'll display them one by one on the screen to discuss them. So let's go ahead and open up the Q&A chat, and then we have at least 4 questions that people just couldn't save. So we'll get to those one by one as well. Wonderful. Okay, let's go to the first one here. Just a moment. We have the Q&A mode enabled and lots of different questions. Let's go ahead and get to one of them. How about we start with the ones that have already been asked, and we'll pin them one by one. So I think Andrea got an answer, but until we organize the questions, let's go ahead and ask this one. So Andrea asks, does the crate system offer a way to prevent dependency hijacking or dependency confusion? And basically, can you tell it which repository it should get each dependency from?
Well, basically, yes and no, meaning that by default, if you specify the name of a dependency of a crate in the cargo manifest, you basically get it from crates.io. This is the default. So as long as the crates live, as the crate lives there, you get it from there. Of course, as long as the language keeps growing and it attracts more people, I'm almost sure that will be attempts at dependency hijacking. For example, they will leverage the fact that you can put a typo in the dependency name and download some malicious code. As of now, I don't know if something has been done in order to prevent this. Honestly, in my experience, and I've been using Rust as of now for a couple of years, for several side projects of mine, I've never had an issue with that.
Okay, thank you. We have another question from Nicola. Let's publish. Okay, we have both of them there. Which tools do you use to build the shared library and the header file from Ruscode? Do you use only Cargo or other tools?
Okay, so this is something that I've actually never attempted as of now. using, or actually, I've done something, but only using cargo. And it was a rather simplistic operation, which was simply compiling a small assembly file for my project and linking it directly. In this case, I just use cargo, since using cargo, you can specify a build script. The build script itself is written in Rust, and there are some excellent crates. One I think is called CC, so double C. It's a crate that allows you to build external C files or assembly files. I've just tried those. I don't know if it supports more complex file types. And it makes it kind of easy, just invoking the compiler for the correct target for your current target, and build the object file, and the Rust will actually take care of linking the library with the final executable. So you can look into that if you want. I can probably write it in chat later. I can give you a link to the crate that I'm talking about.
Excellent, thank you. I think everyone would appreciate that. All right, our next one is Matteo. He asks, how steep is the learning curve? Any particular barrier to entry for developers that have no previous experience with Rust?
So this is an interesting question. So I will not lie to you, the learning curve is kind of steep. It's certainly steeper than any other language that I've had experience with, aside from Haskell. I honestly think that the barrier for learning Haskell is actually almost twice as steep as that for learning Rust. There is no particular problem. The problem is mainly with the fact that Rust uses a different paradigm, a different approach when dealing with stuff like memory management, concurrency, and so on. You may have might have heard about the borrow checker. That honestly, I think, is one of the steepest elements in the curve. Honestly, after 2 years, I consider myself quite proficient in the language, and I think that once you get past that steep hill at the beginning of the curve, you are actually good to go. You will be I think that you will be much more productive in Rust than any other language after you pass this first barrier.
Great, thank you. Let's go to another one. We have, did you know Rust before you spent 3 hours to rewrite C code?
Yes, of course. Otherwise, I would have spent probably 3 weeks. Not 3 weeks, but at least 3 days. As simple as was the code, and despite the fact that the rewritten code was basically a one-to-one transposition of the C code, you need to know something before you may attempt an endeavor like this. But you will not take 3 weeks. You might take a week, but in my opinion, it's worth it for all the guarantees that you get back.
Got it. Thanks. All right. The next one is, how does someone cope with Rust with C++ integration? I mean, how do I call Rust code from C and vice versa?
It's very easy actually to interoperate C and Rust, both calling Rust code from C and calling C code from Rust. There is an entire book written on the subject. It's free online. You can have a look at it. If you Google for Rust FFI, Rust interoperability, you will find it. It's a semi-official book. Let's call it. It's a community contributed book. I don't know about C++ since I have not actually done it, but I know that there is at least one great crate that allows for C++ integration, safe C++ integration, so you don't need to write any unsafe code.
Okay, thanks. Our next one we have is, have you tried a static analysis tool before switching to Rust?
No, and there is a simple reason for that. First of all, I do not have much of an experience with static analysis tools. So honestly, I was quite confident that rewriting it in Rust would take me less time than put my mind to using something that I've never used before. In my line of work, let's call it that. So firmware development, it's not that common, at least in my experience, to use static analysis tools, mainly because you usually do not deal with much dynamic memory. Honestly, in this particular case, I think it was easier and much faster for me to just rewrite it in Rust. If it had been a much bigger software component, let's say 10,000 lines of codes or so, I would probably have attempted the static analysis route first. Not only that, but probably I would have attempted the roll grind approach after that to debug memory leaks and so on.
Okay. Next we have, is there any port for really small architectures, for example, ESP32 or 8266?
Yes and no, in the sense that there is official support for some small architectures such as ARM Cortex cores. They are natively supported as a first-tier architecture, so there is no issue with that. I've actually done at least a couple of projects on the STM32 family of microcontrollers. For the particular architecture that you mentioned, so ESP32 and 8266, they are based on, I think that it's called Extensa instruction set architecture, which is actually not actively supported by LLVM. I know that there is an unofficial port, a semi-official port, or attempt to port LLVM on these architectures, but I do not know as of now the state of the port.
Okay, we have another one. Rust over C.
Rust. I mean, it depends on the context, but after 2 years, I can confidently say that 95% of the things that you can do in C, you can do it more safely in Rust.
Got it. All right. Next we have, was working with no STD tricky?
Yes and no, meaning that if you work with no STD, it means that you are usually programming in an environment where you already are used to these constraints, because you probably come from the C programming language. So no, it was not tricky just because I was used to it. For someone that is just getting started, for example, with Rust programming on microcontrollers, it might be tricky.
Okay. All right. Next question here is, what do you think about sync await? Is that mature enough and or reliable?
I have to be honest, I've not had much experience with the async and await framework. For the small stuff that I've seen and that I've tried, it works fairly well, but I've not tried it in a big enough project to give an opinion about its state of matureness or reliability.
Okay, excellent. Next we have, do you suggest using Rust for other uses like web or games?
So I'll say this, I've used Rust in many different domains. I've used it to write very small microservices. So we could say that I've used it for web, but that will be a huge overstatement. I've definitely tried using it for games. There are actually some nice frameworks out there to write games in Rust. There is Amethyst. Now there is an active development on another framework called Bevy. I think they are actually quite nice to use. I think that there are still some hurdles related to the fact that most game development is done with a specific mindset, and that mindset is comes from the C way of doing things. So, but once you get past those obstacles, I think that Rust can be useful also for game development.
Excellent. All right, next question. Did you notice any slowdown in compilation time for the component after the rewrite? How much slower is usually compiling Rust code versus C code?
Okay, this is actually one of the pain points of Rust compared to C. Rust is infamous for having slow compilation times. For this particular component, which was basically 7 C files, yes, there is a sensible slowdown because the C version basically compiled in almost 1 second. The Rust version took probably 3 seconds, 2 to 3 seconds. For these kind of applications, I don't think it's a deal breaker. But there is active work being done on the compiler to improve the compilation times. And honestly, in my opinion, although they are slow, I cannot deny that, it's never been a deal breaker for me.
Got it. We have another comparison. Rust over Zig?
I haven't had any experience with Zig. I hear that it's a nice language, but I've not tried it yet.
Okay.
I plan to, however.
Yeah, in the future. All right, next, what about OpenCL and OpenGL libraries? Is there a way to use them with Rust?
I don't know about OpenCL, but there are OpenGL bindings for Rust. There are several of them. Even though lately there has been a lot of work in developing some platform-independent graphic backends. So basically, there are some abstractions over the graphic libraries, the underlying graphic libraries. You write a generic code, and that code is basically usable on different backends, be it OpenGL, Vulkan, WebAssembly, I don't know, whatever. The point is that they are generic over the backend being used, and it's actually, from what I see, the way things are done right now. So if you have, for example, a crate that needs to have a graphic backend, it usually uses this graphics library. I think it's called GFX RS, or there is also WebGPU. I can link something later.
Okay, great. Actually, we'll just say for now, we'll finish with the questions, of course, but we can, if there are any links to link later, you can find them in the Discord too. I'll remind you all later about that too. All right, next question here. Did you consider porting the component from C to moderately safe C++? You have destructions and REII to automatically release resources, and some modern C++ features like no discard would have helped preventing the ignoring error code bug.
Yes, meaning that it was a thought that crossed my mind. The problem is that I'm not as proficient in C++ as I am in Rust. So Rust was the first choice in this particular case. However, I think that rewriting it in safe C++ would have had basically the same effect. Yes.
Got it. All right. Let's go to, this might be the last one. I'll keep looking. But it says, do you think Rust can be used for HMI application too? There are some bindings for Qt, or are there some bindings for Qt or other UI framework?
Okay, this is probably one of the fields in which I think Rust may be most lacking. There are, that I know, bindings for Qt, but I don't know about the maturity status of these bindings. I've never used them. I've used the Rust for some graphical, for some UIs basically, but they were very simple UIs, and they were built using EMG UI, which is a C++ libraries for which there are some actually quite good bindings for Rust. They are actively maintained, the bindings, I mean, also the underlying library. I've used it in a couple of projects. They do not share the same paradigm as the usual GUI programming way, meaning that it is an immediate mode way of doing UI instead of being a stateful mode. But I think that for simple UIs, it's actually quite nice. Works quite well.
All right. All right, we've got another one here. What is the state of Rust in Italy? Are there some jobs for Rust developers in Italy?
I honestly don't know. I haven't looked for them at least. I think on our Discord there is a dedicated channel for job advertising. You may probably find something on Rust in the Discord.
Definitely. All right. I believe, unless another question trickles in, that was our last one. If you guys think of any questions later, we can definitely carry the conversation over to the Discord server. We'll keep it up throughout all of the events so that you don't have to say, I never got to ask him. Yeah, we'll look at it there and share links for different things that you guys need as well. All right, so if that's the end, I thank you all for being with us, and thank you, Pietro, for this wonderful time. For everyone here, we hope that this webinar has satisfied all your curiosities. And like we said, we can carry some questions over to Discord, or you can write to us at info@rustlab.it, or you can find us on our social networks. Just search for RustLab and you'll find us there. As far as staying up to date, you can also subscribe to our newsletter to look for upcoming events going to rustlab.it. And, keep on carrying on the discussion. Definitely, we want to see you on the Discord server. We're definitely hoping to keep it up and running throughout the year. So that's it. Last thing I will say is that we have the next RustLab event on April 22nd, which is a Thursday, called From 3 to 96, How to Beat Git in Its Own Game in Rust by Sebastian Thiel. So hope to see you all with the next event, and thank you all for coming. All right, see you next time.
Thank you, everyone. Thank you, Latara. Bye.
Thanks. Bye, Pietro. Bye, everyone.